So here is an example what we have taken. Here is where we call it as an example of neural machine translation with attention. This takes a sequence to sequence model like encoder decoder for Spanish to English translation. So what you do is, after you train the notebook, you should be able to take a Spanish sentence and return the input English translation. Like, for example, if you give todavía están en casa, you should be able to get the English translation. Because what it shows also is, it shows that there is a 1:1 mapping absent. In fact, many:1 mapping present in the words. If you see here, the attention when you try to create, the model is showing that if you see still, it is talking about if you see at, it is talking about mapping to multiple input combinations. So while this is not as clear, but if you take more examples, longer examples, you should be able to get the actual plot. So what you do is, you first take the data set, you load the data set, convert Unicode to ASCII, pre-process the data, then you do all the sentence pre-processing as you remember what you were doing earlier in natural language processing. Then you create the examples as pairs, English, Spanish. Once you create the language, you train the language, but what you do is, you only take the number of examples to 30,000 instead of the full 100,000 samples which has been given. So you take the number of examples of 30,000, you load them. Now you do the test train split with 80%, 20%. So what you do is, you create the corresponding index for each corresponding word, so that you know that at what position is each word. As I said, all these models, when you involve text, you cannot work with pure text. You have to convert them to numbers. So what we will be using is, we'll be using the positional index, or the word index for each word will be the corresponding input for the representing that word. And here we're developing the attention model. For example, you see here, if you see the output, Je suis étudiant, and if you see the attention vector for that word J, there is a lot more focus on I, but there is also some input coming from am, while very little is coming from A and student. So this is what is the context vector, which is attention vector, which is learned from the attention vector corresponding to the word output J. Similarly, you will receive the attention vector for suis, étudiant, etc. So what you need to understand is, the encoder plus decoder plus attention model is the corresponding output which you get, which is used for the final translation. So there are some different kinds of attention models. Specifically, the attention model which is used here is what is known as Padmanabhuni attention, which is basically a simple relative weight of the particular T on specific part of the input sentence divided by sum of all the scores, exponents of scores of that target word on all the other words. So in that sense, you need to understand that this is basically a specific attention model. There are several other variants of the attention models which have been there in literature. So what you do is you first get the attention weights, then you take the context vector as sum of the attention weights, the intermediate vector, and output, embedding output is the input to decoder X, which is passed through the embedding layer. And finally, the merge vector is the embedding output and the context vector. Embedding output is the output you got till now, and the context vector, which is the attention model taken into account to predict what is the next in the sequence. So if you see in the model, when we had talked about predicting the attention model, we are talking about predicting the YT not just in terms of XT with attention model, but also on YT minus 1. So YT minus 1, which is the previous part of the output, and the attention model applied on top of the encoder, decoder applied on the intermediate model, is together predicting the next character or the next word. So that's exactly what we're coming here, which is basically the output and the context vector is given as the merged vector. It's not like we're only giving the context vector as input, it's also taking the previous part of the input. So what are the steps? We pass the input through the encoder, which returns encoder output and encoder hidden state. Then encoder output and encoder hidden state, and the decoder input, which is the start token, is passed on to decoder. The decoder returns the prediction and the decoder hidden state. Then decoder hidden state is passed back to the model, and the models are used to predict the calculus. And then this is basically used to decide the next input to the decoder. And then the next predictor target is passed on as the next input to the decoder. And finally, you use the gradient computation and use the optimization and back propagate to update the attention model and the weights of the LSTM. So I just want to show you the final output. So while I may want to connect it and do it again, what has happened is this takes a huge amount of time. What I will do is I will store it on the network and request you to go through it. I would have liked a lab to be explaining in detail the running of this, but from a conceptual perspective, think about it like the model is looking at actually implementing this particular slide in more detail for the specific language translation model. I'll leave that as an exercise for each of you to go through it, because from a theoretical perspective, there is not much. It's more about the nuances of the specific implementation of the attention model and how this has been proposed in a specific application. So neural machine translation is one very specific application of the encoder decoder model with attention